Hello, hello, hello. How's everybody doing tonight? Thank you for joining us at our third review session of the year for CP164. So tonight's review session is going to be focused on linked data structures, specifically focused on linked lists, linked priority queues, and then some linked recursion as well. Your hosts tonight are going to be me and Noah. Mila isn't here. She's having a few troubles with her hardware, specifically an incompetency in finding her charger. Yeah, not much more to say about that really. So let's just jump straight into it. If you would like this on your Laurier experience record, I would highly suggest scanning this QR code. I'll leave it up on the screen for a bit. Or you can use this link alternatively, it'll take you to the same place. But just fill out the type form either now or after the review session to get this added to your Laurier experience record. It'll go on Navigator, it'll give you an easier time. The co-op, stuff like that. So I'll leave this up here for a little bit. Sorry if my chair is squeaky, guys. I like bobbing up and down because I don't know. It reminds me of my mom like rocking me in my when I was a child. Whatever. Enough mommy issues for today. But just like if my chair squeaks, don't make fun of me. All right, I'll keep this up for 30 more seconds. If anybody needs it, I'll go back to it afterwards. If not, and if I don't, actually, you can just go look at the VOD afterwards as well. It'll be posted on Twitch, and you can scan it from there. All right, so let us get started. So let's look at the future session roadmap really quickly. So this is our third review session. We've already done the midterm review and our first review session of the year. The next one is going to be looking at some more linked data structures. And then our fifth review session is going to be our final review session of the year. It'll be based on the final exam. So we're going to be looking at all the stuff we covered, as well as some new topics that have been introduced between the fourth and fifth review session. And we'll answer, obviously, any questions about the final that you guys may have. This isn't confirmed yet, but we may be handing out a practice final exam. I know we did that for CP104, that you guys can complete. And yeah, stay tuned for those on the Instagram as well as the Discord for the dates for those review sessions. All right, so looking at today's agenda, we're going to be looking over linked structures, as I mentioned before, linked lists, and then I'll pass it over to Noah for linked priority queues and linked recursion. So let's jump right into linked structures. What are they, and what are some common use cases? So, what are linked data structures? Linked data structures are built with multiple nodes, where each node is connected using pointers to the next node in the structure. So, what does this mean? So, a node in a linked list has a value attribute and holds the value itself of that node, and a next attribute that holds a pointer or a reference to the next node within the linked list. So you can think of a linked list or a linked structure as a chain, for example. Each of the chain links is a node, and it connects to the next node. So some common use cases, these are data structures that we use linked structures with, linked lists, linked queues, and then these are going to be covered in today's review session, but later on we're going to be looking at binary search trees, which are an example of nonlinear linked structures. As we can see here, they're not going in just a straight line. They kind of diverge into two paths, so a left and a right node for each parent node. And then a real life example of kind of a linked data structure would be a blockchain, as it contains data that has a hash of each of the block or the node before it. So it kind of connects all of the data together using linked structures or blocks, making it a blockchain or a linked block structure. So yeah, let's look at kind of a practical example of what a linked structure would be. Let's think of a railway system that can only go in one direction and doesn't contain any cycles. What I mean by cycles is if we start in a point, we can't get back to that point. So we start in Toronto over here because Why not? Um, the city would be the value of the node. So think of each train station as a node. Each destination is a node. The value of the train station would be the city, being Toronto. And then the next value would be the node itself. This node itself would be the next value. So then the next one, the city is Kingston. That's the value. The next is the node of Ottawa. This node contains a city or a value of Ottawa, and the next is Mississauga. And it keeps going on, as you can see here. So that's kind of how a linked data structure um, shows its data or stores its data, rather. So it always has a value and then a way of linking it to either the next node or the previous node, which we can look at as well afterwards. So linked lists. What are linked lists? It's just a linked implementation of a list data structure. Each node, as we said before, has a value and a next value. So in this class, we kind of think of linked lists as the head of a linked list, which is the first value. It'll be the first node, which will contain some kind of data, and then a next, which will contain the next node, and so on and so on and so on until we reach null when we know we're at the end of the list. So this is something that we call a singly linked list. This coming from the fact that it only goes in one direction. We only have a next value. Something like a doubly linked list, for example, would be something with a next attribute that points to the next node, as well as a previous attribute, which points to the node prior. So you can see how you could kind of implement that. You need a little bit more. So let's look at an example of a linked list. So we'll look at the example of how to implement it and then kind of using it within a scenario here. So we start off by defining the list node class. So all it is an initialization function that stores the data of value and next, like we said. So we just give it a value and then a next value. And that'll be how it's stored, just self.value and self.next. And then we can create a list class. We have a front, a rear. So front will just be the first node, rear is going to be the last node, and then count will just be however many values there are in the list. This isn't necessary. This initialization function of creating the actual list isn't necessary, but it's a better interface for communicating with the linked structure. We could have a linked list of just list nodes without all of this initialization, like just having a list node with a value being 5, for example, and then the next value being list node with a value of 5 and then null as its next. So we could have just that, but it doesn't really give us a good example or a good interface to work with that list data structure. So if we want to use the list as a proper data structure, we should initialize a list data structure rather than just a list node. So we can see here the isEmpty function. We can just check if self_front is none. So if we haven't added anything to the list, it's obviously still going to be none. So we can just check if that's none. Or alternatively, we can check is count 0. That would also work. And then the length of the list is just going to be, we're just going to return self.count. As we said before, count is going to be how many elements are in it. So append starts to get a little bit more complicated. Like we know in a normal list, we can just do list.append. Simple as that with the value. So here we're going to have to do a little bit more just because we can't really it'll be kind of complex to add it. But let's look over this code and see what's going on. So we give it a value. This is the value we're going to want to add. So we can say a new node is equal to list node of value and none. So we're creating it to go at the end of the list because that's what append is, right? So our next value is going to be none because it's going to be the last value in the list. So we check if self_front is none, and if that is the case, then if self_front is the case that it is none, that means there's nothing in the list. So the front is going to be the node as well as the rears. The rear is also going to be the node. So we can see here, if self_front is none, then we say self_front is none. is the node, and then we skip over the else because obviously we already used the if, and then we say self rear is node. So the front is the node, and then the rear is also the node. So that's the only node within the list, and then we add to the count. So now we got to check if there's already something within the list. If this fails, if self front is not none, we have to say self rear next is equal to node. So if we think about it, we have a list, a linked list, and the last value, we want to add something to the end. So we want to say the rear's next value is currently none, right? But we want to set it so that the rear's next value is connected to the node that we're inserting. So we say self.rear.next is the node. So that's why we say self.rear.next is equal to node. And then we also have to set a pointer so that we know what the new rear is. And the new rear is going to be the node. So now we have this, the original rear is going to be the second last one. And then the new rear is going to be the very last one. So that's why we have to do rear.next is equal to node, because we want to connect the previous last with the current last, and then we set the current last into the self.rear inside of the data structure itself. All right. I know that was a lot of information thrown at you all at once, but I'm sure you're kind of getting the hang of how we have to work with these linked data structures, because we can't just traverse to the very end without going through kind of the elements of it. So, yeah. Let's look at peak, for example. So peak, we want to look at, we're given an I, and that's the index of what we want to look at. So current, we're giving it a current, and that's just going to be the front, because we have to go through every single item in the list until we get to the index that we want. So if I is less than 0, I equals self._count plus I. So why do we do this? Because we want our peak to work how normal list indexing works. So what I mean by that is, if we were to give a list index -1, everybody knows what that does, right? We get the last value of the index. So we do the same thing here. Self.count, let's say, for example, is 5. So that means we have 5 elements of the list. If we have I is -1, we want to return the 0, 1, 2, 3, 4th element of the list being the last. So here we say self.count, count is 5, -1 because I is -1. So our new I is going to be 4. So here we initialize a counter variable j. While j is less than I, current equals current next. So while our counter is less than what we want to go up to, go to the next value in the list. And then once we break out of this while loop, meaning we get to our I, then we just say value equals current value, and then we return the value. And then return values isn't too important. This is just for our printing sake. It just takes every single value, appends them to a list, and then prints them out. All right, so let's look at this data structure being implemented into another data structure that we can take a look at. So we can say here, initialize our diary function as our entries are going to be a list, being this linked list here. So we define the new entry as self.entries.append because we just want to append to the end. That's fine. We already implemented that, so this function will work just fine. View entry, we can peek at a certain day from the entries, and that'll work just fine because we're just peeking from a list that we implemented before here. And then return entries would just be return values. And then we all know how to work with a data structure like this. So diary equals diary, first entries equals this list. We convert this list into a linked list by saying, for I in first entries, diary.newEntry is of I, which means we traverse through this list. I is going to be each item in this list. We add the new entry to our diary data structure, which is just a linked list in reality. And then we can just say return entries, diary entries so far. And we want to look at diary entry 0. So we can just look at diary.view entry of entry. And so what we're trying to explain with this example here is that just because the linked data structures are implemented in different ways, they still need to function in the same ways as their non-linked counterpart. So if we were to implement this diary function, or sorry, this diary class using an array, not linked, just a normal list, we would initialize it as self.entries equals just square brackets or an empty list. And then we'd say the same thing, self.entries.append of the value, self.entries.peak. We wouldn't say peak, obviously, because we know we have list indexing. So we just put the square brackets. And then return entries, we would just go through all of them and print out the values. So we can see here that regardless of how we implement the data structure, it should still work the same way. All right, so that kind of covers it for linked lists. If you know how to work with lists and you kind of understand the concepts of linked data structures, you should be just fine implementing a linked list. So now let's look at something like a linked priority queue. So I'll pass it off to Noah, and he can guide you guys through what a linked priority queue is and how we can implement it.
Hello, everybody. So now we're going to look at linked priority queues, what it is, and common use cases for this data structure. So what are linked priority queues? So each node has a value and a next value, and nodes are sorted based on their priority. So the example that I remember we were given back in first year of a priority queue could be like the line when waiting for a hospital emergency room, or as they say in the UK, the queue for waiting for a hospital emergency room. But the priority queue, so the idea is, let's say there's a person who is slightly ill, and there's a person who is in immediate risk of death. Even if the person who's at immediate risk of death came in later than the person who's slightly ill, the person who's at the immediate risk of death is given a higher priority because they're about to die unless they get medical attention that instant versus the person who's slightly ill can not get medical attention for a while and still be fine. So that was the example we were given, and that makes sense with priority queue because, for example, in this hypothetical I just gave, so the person who's slightly ill, their like value would be their level of sickness, let's say, which is slightly ill. The person who's about to die, their like value would be how poor their state of health is in this instant, which is, at a very high risk of death. And then the person who's slightly ill, their next would be the person at the front of the queue, which is the person who's about to die. The person who's about to die, they wouldn't have a next because they're at the front of the priority queue. So it's just an example of how linked priority queues work and some like real life application of that idea. So a comparison to a standard queue, it's more difficult and less efficient to insert a node. More difficult because it's just sort of like in your head, more difficult because you have to account for priority with your insertion. So the code is just more complicated when you implement it, and less efficient as in like in terms of big O, it's going to be a worse big O because as you account for more things, you ultimately do more work. And this is reflected in the higher complexity of the algorithm for insertion to a priority queue compared to insertion to a like normal queue. And we must iterate through each node in the queue, searching for the proper positioning based on its priority. So that means that we have to look through the entire queue to make sure that we are putting something as proper priority. We don't want something to be placed earlier in the queue when it should be placed later based on its priority. We also don't want it to go too late into the queue when it has a lower priority. So these are things that we have to account for when we handle the insertion to a priority queue. So here's an example on this slide of the priority queue being a linked priority queue, being implemented in Python. So here there is a node. The node is initialized. The node, as you see, has a value and a next. So the value is as a deep copy of the value passed into the init function. And the next is just going to be the next node that it sort of points to, I guess you could say points to. And then there's also a class priority queue, so not the node, but the data structure itself. And for the initialization function, its front is initialized to none, its rear is also initialized to none, and its count is initialized to 0. And then below, we have implementation of inserting to the priority queue. So let's go through this algorithm. So first we set up a node called previous, and we say it's none for now. So I guess it's not technically a node yet, just a variable, but we're going to be storing a node with this variable. And then we have another node variable called current, and we're saying that's equal to self.front. So I think we understand what that is now. So now we have a while loop. While current is not none and value is less than or equal to current.value. So this loop continues to iterate when the following two conditions are met, that current, so self.front at this time, is not none. And the value, so value being the value we're trying to insert, the value we pass as parameter, that must be less than or equal to the node that we called current. It must be less than or equal to that node's value. So as long as these two conditions are satisfied, the following is repeated. The node that we'd called previous is now, instead of being none value, it is the node that we called current. And then that node that we were calling current is going to be its next. And then we go back and we check while current is not none and value is less than or equal to current.value. And as long as both these conditions are met, we go through this loop again. So once we go through this loop, now this loop here is going to stop when one of two things occurs. Either the value is greater than current dot value, either that is the case, or another thing that can stop the loop if that never happens is if current becomes none when current goes to current dot next. So that's how this loop stops. So in any one of those two scenarios, it would end that loop. Oh, sorry, went to the wrong slide. There. Then once that loop is over, we say node is equal to PQ node of value and current. So we're making a new node, and we're saying that its value is the parameter value that we passed in, and then its next node is current, and we established what that node current will be from the while loop. So it's either gonna be none if we never encounter a value of the greater priority, or once we encounter a value of the greater priority, then it'll be the node containing that value passed in as our next node in the parameter for current in that PQ node init function. So then we do if self.front is none. So we're checking if the front of this priority queue is none, so we have an empty priority queue, let's say, then we say self.front is node, self.rear is node. Why? Because if you have an empty priority queue and you have only one node, think about it, that's both the front and the rear, right? Elif previous is none. So now we're saying if the node that we called previous is none, so previous would either be equal to the last node in the priority queue, if there was never any value that's greater than current dot value, or previous would be equal to the one that's before the node of greater value. So it's either one of those. So if this node previous is none, then we set the front to be node, because we're realizing, okay, so if the node before this is, if there's no node before this node, then this node must be the front node. That's what we're saying. Next, we're saying elif previous is self.rear. So if that node previous, which I just talked about what it is the rear, then we're saying that the rear's next is node, or we could also be saying previous dot next is node. I believe that would work too. And then we establish that the rear is really node, so we say self.rear equals node. And then else, if it's none of these cases, we just say previous dot next is node, and then we increment the count by 1, and we don't return anything. So that is an implementation of the insert algorithm. If you take a look at your Eclipse and you go and check your normal linked queue, not your priority queue linked, and see the insert algorithm for that, I have a hunch it'll be simpler unless you maybe really wrote that one in like a weird way or something, but that would be on you, I guess. But yeah, so now the next topic we're going to discuss is linked recursion, or recursion broadly. We're going to show how it applies to linked data structures with linked recursion. So let's talk about it. So recursion, what is it, and common use cases? So what is recursion? And we talked about this in the previous review session, but we'll just go over it once again. So recursive functions are functions that call upon themselves, and recursive algorithms have two main parts. The first is the base case, where you make where the recursive call ends, returning to where you started. And the second time, which is the recursive cases, where the function is called and passed a different parameter or modified parameter value than what was previously passed to it. So here's an example of a recursive function to calculate the greatest common denominator between, between integers m and n. So here, the doc string, let's read this. Recursively find the greatest common denominator of two numbers. Use answer equals GCD m comma n. Parameters n and m. Returns answer. So first we initialize the answer to be equal to 0, and then we have an if statement. If m mod, I'm going to use Martha and Nancy because it's hard to understand. If Martha modulus Nancy is equal to 0, then the answer is equal to Nancy, because it's finding greatest common denominator. So if it divides evenly, then the answer is equal to that divisor, which would be Nancy. Else, answer is equal to the greatest common denominator of Nancy and Martha mod Nancy, because that we keep on going to a lower and lower and lower divisor until we find a divisor that evenly divides. That's how you recursively find greatest common denominator. So now, what is linked recursion? So linked recursion is used to directly traverse through linked data structures. So linked recursion uses the same thinking or the same algorithm as normal recursion, as in there's base case and recursive case. However, linked recursion typically requires the use of an auxiliary function, and it takes care of the recursive cases and is only called by its parent function. The aux function allows for easy traversing as it only works with the node portion. So here's an example case. We're going to recursively reverse a linked list. But yeah, so, and here we also have an auxiliary function. So def reverse ourself. So reverses the order of the elements in list, and returns the contents of list to reverse in order with respect to their order before the method was called. So if self.count is greater than 1, because if you have a list of just length 1, or even an empty list even, you can't reverse it. There's no operation to be done. So we say self.rear is equal to self.front, and self.front is equal to the auxiliary function none and self.front. And then here is our auxiliary function. Def reverse our aux, self previous current. If current is not none, we say this node called temp is equal to current.next, and then current.next is equal to previous. And then we do previous is equal to self reverse our aux, current, and temp. And we keep on doing that until we basically keep on reversing the order of like the next and the previous and stuff, until using recursion we have fully reversed that list. And then yeah, that's how we recursively reverse a linked list. So now on to the Kahoot.
All right, I know this is everybody's favorite time. I don't know why this picture of Drake taking a shit is on the slides right now.
I admit it isn't me. It isn't me, I admit, but yeah.
Guys, Noah's a Drake stan, so please clown him in the chat right now. He does not deserve to like Drake in peace. Let me make my camera smaller.
You used to call me on my cell phone.
Give me a second. Let me move my camera so that you guys can scan the QR code. Join this game up, guys. It's gonna be a good one, I promise. And if anybody wants us to go over anything that we reviewed, I know that we went fast today, and I know there's a lot of advanced topics, but if anybody wants me to go over them again, I shall. But join this game right now. It'll be a good time. I know there's only 5 people in chat right now, but if everybody's in here, we can still have a pretty competitive game. Here, I'll even join myself. I won't really, just to boost the numbers. Sorry, I get really insecure if, like, you know, it's like likes on Instagram, pretty much. But this one really, really impacts my self-worth. So everybody join up, please. Oh, who's that? Guys, stop. It's me, by the way. Alright, so I guess this is going to be another Kahoot for the people watching on VOD, just as a practice, since we have 2 people and one of them is me. Alright, I guess let's get started. Alright. So, what is a real-life example of a linked data structure? I'll only answer after Kyler, I guess, just to make it fair. Yeah, so that is correct. A blockchain is a real-life example of a linked data structure because, like we explained before, each block in the blockchain is connected somehow or linked to the next one or the previous one. A hospital queue is a data structure. I know Noah kind of explained what a hospital queue is to explain the priority queue. However, I wouldn't really classify it as a linked data structure just because you aren't holding hands with the person in front of you. In that sense, it would make it a linked data structure, quote unquote. But a normal hospital queue is more of just a priority queue rather than a linked priority queue, for example. And then phone contacts and lists of movies. List of movies would be more of an array, a list. And I'd say phone contacts could be more of a list as well, or a dictionary, however you really want to look at it. But they're not really connected to each other in any way. Like each of the nodes, even though their information might be kind of linking to a different place, they're not connecting with other nodes, so to speak. So, yeah. Which data structure is most useful when converted to its linked counterpart? Okay, so the correct answer is list. This is a very important concept. Linked lists are pretty important. They're pretty much the most commonly used linked data structure other than trees, which we'll look at in the next review session. They're the most commonly used linearly linked data structure. It's a mouthful, but that's just what it is. So it's most useful. So let me explain the other ones to kind of give you an example about why they aren't so useful. A dictionary isn't very useful because we get no use of connecting each of the nodes to each other because they're kind of self-containing in a sense where the only thing that really matters is the relationship between the key and the value. So that's the reason why a linked variant of a dictionary doesn't really make sense as a conceptual thing. A set would also not really be viable Well, it works. A linked set is fine, but we just don't really come across it too often. So I would claim its utility is not as high as a list. But obviously, a linked set makes sense, and it may be something that you guys have to implement in the future. Um, it's the same as a list, obviously, except there's only one value that can be the same. And then a tuple pretty much in Python is a list that can't be, it's not variable in length. So if you were to initialize a tuple with three values, you can't add another value to it. So that kind of defeats the whole purpose of what our linked data structure is. We can't really, um, because our linked data structure is made out of nodes, we can only kind of create them one at a time without going too deep into like hard coding it, like list node and then value. Next is list node value. Next is list node value, and so on and so on and so on. It'll like always be kind of a one by one thing. It'll be the whole point of a linked list is it being dynamic in how much memory it uses and dynamic in how big it is. So a tuple kind of just defeats the purpose of a linked structure entirely. So that's why list is the most useful when converted to its linked counterpart. Oh no, I am currently ahead. I'll get the next one wrong, I promise. So this one's a multi-select. How does linked recursion vary from normal recursion? Okay, so the correct answer was base cases and traversing through elements. So let me explain why the other ones are wrong before we dive into why these ones are correct. Oh, I just realized my camera's in the way. Let me just delete my ugly mug off this face. I mean, off this. Hide. Okay, there we go. That's better. That's better. All right. So, amount of recursive calls. This would has to be the same. It always has to be the same. And end result as well, they have to be the same, or we defeat the purpose of converting it to linked recursion, or like converting between the two. If they don't have the same result, we're doing something wrong somewhere. So that accounts for amount of recursive calls. We should have the same amount of recursive calls, and we should have the same end result always, because we're doing the same algorithm, except we're doing it with a different data structure, with a different interface, doing it in a different way. But the algorithm itself, if we were to write it out as pseudocode or without, for example, without using any of the syntax of the data structure, we would get the same exact thing. So the amount of recursive calls will be the same and the end result will be the same. So that means that the ones that vary are the base cases and the way that we traverse through the elements. So why traversing through the elements is different is because the way we traverse through a linked data structure is different than how we would traverse through a normal data structure. So for normal data structure, for example, we can say, I don't know, we can splice off the last thing, for example, or splice off the first thing and then run it through the algorithm again. So that's kind of how that works. But with a linked data structure, we just say self equals self.next, and then that's how it works. So we're taking the node that we're currently at, and then we're making it the next node. So that's why it's kind of different. Then the base cases are different because we check when the linked data structure no longer exists, rather than the data structure being empty, because it still does exist when it's empty, but we're checking if it's none, because once we get to the very end or a next value that is none, we know that we need to stop. But for something else, a list, for example, I'm kind of taking linked list and list as the main example. We check if the list is empty, that's our base case. And then if our list node is equal to none is our other base case. So that's why the base cases are different, and that's why traversing through elements are different. But the amount of recursive calls are the same, and the end result is the same. Again, because we're using the same algorithm, just kind of formatted or done differently through the data structures. All right. So why are data structures or linked data structures considered linked? Is it a reference to Zelda? Does each value node reference the next node? They are immutable, or they are implemented using a link editor? Yes, so that is correct. Each value node references the next node. So obviously it's not a reference to Zelda. I mean, it'd be pretty cool if it was, but I don't really think it is. Linked data structures, their whole purpose is to be mutable, so they are not immutable, so that's also incorrect. And they are not implemented using a link editor. I'm not even really sure what a link editor does. I'm assuming it's a thing. Sounds like a thing, but I don't think it has anything to do with linked data structures. So the correct answer is indeed each value node references the next node. All right. So what is a doubly linked list? We briefly discussed this. Hopefully you guys remember. Yeah, so that's the correct answer. It is a linked list that has both a next and a previous node reference. So each node references the node that came before it and the node that comes after it. A singly linked list can be a linked list that has two values in it, so that's not correct. We can have two values within a linked list, but it still points only one way, so it'll still be singly linked. A linked list that connects the front to the end, we could have that as a doubly linked list, but a doubly linked list that's not the definition of it. And then a list that requires two indexing calls to retrieve values, I don't really know what that means. Just kind of a bogey answer. I know nobody answered that, but if you were thinking that, that's not correct. So how does a priority queue differ from a normal queue? Yeah, that's correct. So the value with the highest priority exits first. I know in the example we showed, this was also true. The values are sorted highest value to lowest value. So we were considering that the value was also the priority. This isn't technically always the case. We can have a different, like a separate priority identifier for each node, and it should be based off of that. But obviously, if we define it as the value being the priority as well, then this would be correct. It's obviously not more important than a queue, and the value with the highest priority exits last because it's special. That's not true. It exits first. Okay, so true or false? All native data structures in Python can be converted to linked data structures. True. Oh. Okay. So, I mean, again, this is up for a matter of discussion. If we like to consider tuples in this case, we could have them linked again, but they really defeat the purpose of a linked data structure. Can they be converted to a linked data structure? Yes. Does it make sense to convert them to a linked data structure? No. Dictionaries can be converted. Again, it doesn't really make sense because the only reference that really matters is the key to the value. And then a set, like we discussed before, can be converted, and a list as well can be converted. So the correct answer in this case was true. And let's move on. So which loop is the best to use when traversing through linked data structures? Is it a while loop or a for loop? Oh, okay, yeah. So while loop is the correct answer. Um, we know that it's a while loop because we have to check while our node is not none. And we don't really have, like we do for a linked or a normal list or a queue, for example, we could have a length of like how many values there are, but we don't necessarily have that for linked data structures. So we're only relying on if they exist or they don't exist. So because it's conditional in that sense and our values are changing every time the loop um, executes, that's why we have to use a while loop. If we use a for loop and say for length in the linked list, that doesn't really make sense unless, of course, like we did in the example, we implement a data structure on top of the list node that stores its length. In that case, we can say for I in self.count, for example, and then do it like that and then keep going next. I wouldn't like use that for everything because it doesn't work. So the while loop is definitely the best loop to use when traversing through linked data structures. And it's the most effective because it's conditional and we can stop at a certain point and not just keep going until we get to the end of our count, if we even have a count implemented. Oh, getting interesting. So how many items can be stored in a linked list? Yeah, so it's unlimited. Like we said before, um, linked lists are a dynamic data structure. We can just keep adding to them. The more things we add, the more space they'll take up. We can have an unlimited amount of items, unlimited amount of nodes, values, whatever you want to call them. All the other answers are kind of, they don't really mean anything. They're just random. So unlimited is the correct answer. Um, Obviously, unlimited is not literally unlimited, but unlimited um, in a practical sense, right? You can obviously put a million things in it, but are you ever going to put a million things in it? No, probably not. It's obviously just as many as your heart desires at the end of the day. If you want to put 1,000 things manually in your linked list, by all means. Um, but it's just the viability, right? If your computer can handle a billion nodes worth of memory, then by all means go for it. Like it'll work. But yeah, it's unlimited in the technical sense. So okay, so linked data structures are made up of what? Values, nodes, lists, or integers? Yep, that's correct. So, like we discussed many, many times in today's review session, data structures are made up of nodes. Um, yeah, I mean, they're not made up of integers. We saw that they can have integer values, but the data structure itself is made up of nodes that contain, like we said, a value and a reference to the next node. Um, yes, okay. So we kind of know who's on the podium already. Third, yo, congratulations. Well done. Second, hey, thanks. And first is Kyler. Congratulations. I messed with the eagle. But yeah, we'll keep this Kahoot music on because it slaps. But if anybody, let me turn up my face cam again. If anybody has any questions, whoa, light is blinding. If anybody has any questions in chat, I'll answer them. There aren't too many viewers in the chat right now, but I'll answer any questions. But yeah, thank you to all the people that joined us tonight. If you missed anything throughout the session and you want me to go over it now, we still have a couple more minutes left. And if not, you can go over the VOD again if you'd like. It'll be on Twitch. So I'll give it 30 more seconds because I want to listen to the Kahoot music. Okay, since I don't see any more chats rolling in, I guess we'll call it there. Thanks everybody for joining us. Oh shit, no. I thought I had my camera like this on my screen and I didn't notice I was doing a little funky dance and everything. Wow, you guys really missed out. I'm sorry about that, but I bid you all farewell. Uh, Good luck on all your endeavors. I'll join you guys in 2 weeks for our fourth penultimate review session. There'll be some more linked data structures, um, linked data structures that are not linear. Whoa. Um, but yeah, be sure to come out to that. It'll be on Twitch as well, 7:30 to 8:30, same time, 2 weeks from today. So make sure to mark your calendars. And yeah, I bid you farewell. Everybody have a good night. Thank you so much for joining me. Noah says thank you too, but he's muted. So,
Bye, everybody. Thank you.
all right, good night, guys.